Welcome back, everyone. Real hardware, real sensor, real data. Hopefully most of you came by train actually today. Yes, is that true, everyone? Yes. So who makes sure the trains are operational when they should and the maintenance is done at the right spot? All of you guys, that's funny. So the next talk, our next two guests, they work for Kistler. They do the best, probably the best sensors in the world. We have Schatte. He's a business developer, project manager, innovation lab, and Stefan Weber, data scientist. And they want to show you how you can do the pipeline from the sensors over your assets to the visualization with data science. Welcome on stage, please. The floor is yours.
Thank you. There we go. All right, thank you for the introduction. So we'll briefly tell you about a project that we have realized together with the AGO Verkehr AG, where we actually used accelerometers to get some information about the state of the track-wheel interaction, and wheel health. And I look forward to showing you what we have done. So briefly, I'm going to go over the motivation, the rail system's operational goals. For some of you, this is going to be very repetitive, but maybe not for all. Then we'll look at what our system actually is, what the general architecture is, and the general functionality. And then I'll hand over to Stefan, who was the data scientist in this project, to talk a bit about the algorithms behind and the way we did it, and also present the results. And then I'll sum up what we have seen and learned. Good. So let's have a look at the picture here on the right. Perhaps some of you have known about this rail incident in East Palestine, USA. So what happened there actually was that there were wayside monitoring systems monitoring the temperature of the bearings. The train went past one, then 50 kilometers later, it went past the next one. The bearing had heated up by 120 degrees Celsius, and then indeed the braking process for the train was initiated, but it was too late. It caught on fire and was carrying flammable material. And so this is, let's say, one example, which I'll get to a bit later regarding temperature. That safety is always, let's say, the most important operational goal. Aside from, of course, system costs, reliable operation, high availability, and environmental impacts such as noise or pollution. And of course, passenger comfort is also one of those things, depending if you're a passenger carrier or not. But just as an intro. So if we look a little bit at the maintenance costs, they can be separated into direct maintenance costs, which are the costs that are necessary to conduct maintenance operations. So the materials and the efforts to perform maintenance on your assets, be it the tracks or the rolling stock. On the other hand, we have the indirect maintenance costs, which are costs which result from not doing maintenance, or which can happen at any point in time, which we want to keep low by doing maintenance. So those are unplanned failures, suboptimal efficiencies by friction, for instance, or even effects on the surroundings and the environment. So, I mean, for most of you, this is probably not new information, but by enabling condition-based maintenance rather than just preventive maintenance based on just some statistics, how long something has already been in operation and should statistically be replaced, we can enable a couple of advantages, such as using the asset longer, while at the same time detecting faults early onwards. If we think about the train example earlier, then precisely identifying what was the error and which maybe spare parts are needed in case of maintenance, and also making everything more plannable. One thing that I would like to add, though, it has a cost too. To do this, you need systems, you need software, and you have to really, in each case, look at what are we trying to solve, what are we trying to make more economical, and see what the cost of the CBM system is in the background, just as an input here. Good, let's look at some measurements, and here we go back to the temperature as a physical quantity. So temperature changes in a moving machinery as a result of vibration and friction. It is transmitted through the machinery via thermal conductivity. It is a rather slow process, and it's hard to identify if something heats up where it comes from, because the heat simply diffuses through the solid, and you can see it after a certain amount of time, but you can't locate it. Compared to that, vibration, acceleration, if you sample it high enough, it moves through the solid at the speed of sound, so you can immediately see where origins of parasitic vibrations are, and of course by characteristic frequencies in the signal you can identify also which components are off if you sample it well enough. So we as Kistler of course think that, and we believe that vibration there has an advantage over temperature. Again, a side note, you have to look at when it is the more economical choice, a suitable choice for each use case. But if we look at the example before, via vibration measurements on board, for instance, it may have been possible to prevent this incident. Good. So what are we looking at specifically? We have divided it into 3 categories. We are not the rail specialists, we're the measuring specialists, but so we have divided the problem into 3 different focus points. One is rolling stock health, the other is track wheel interactions, and finally the other one is infrastructure health. And Stefan will be showing an example of the first 2 later on. Yeah, if we look at which system we have to investigate these things, it consists of accelerometers mounted to the bearings on the wheel set with a data acquisition system, as well as a GPS. The signals goes to an edge computer, which kind of pre-digests the data, cuts out unnecessary parts, performs some initial calculations, and then sends the data to the cloud, where the data is then stored, analyzed, maybe converted into some format that has a value to a customer. If we think about what is raw acceleration data, no one can interpret that, whereas at the end of the day, you need something that's interpretable, understandable for the end customer. This project was done, as I said before, together with the Aargau Verkehr AG, and the idea of this system was to identify squeal or flange friction events and see if they correlate the way they wanted with the railhead conditioning mechanisms. And then there are a couple of other use cases which we are still looking at. Those are the ones in parentheses, like gearbox health, bearing health, which we are still exploring. Good, and with that, I'll hand over to Stefan, who will go into some of the details on the algorithm and the sensors. Thank you.
Thank you very much, Gerrit. I hope you can hear me well. So, as Gerrit already mentioned, we measure acceleration and the GPS position of the train. And in our current setup, we have 4 acceleration sensors, which are mounted to the axle box, which you can see on the left side of the slide. And the acceleration is sampled on a really high sampling rate, so with 50 kilohertz, which produces a lot of data in a short amount of time. And one example of a 1-minute file you can see in the middle of the slide. And we measure the X, Y, and Z direction. And together with that, we have a GPS module where we know the exact position, the longitude, the latitude, and the speed of the train. And so this data needs to be put somewhere to analyze it and to visualize it to the customer. And again, from left to the right, we have the acceleration sensor and the GPS module, which the data is pre-processed and merged on an edge device, in our case a computer, and then it's uploaded to the cloud. And as soon as the file is uploaded to the cloud, a function is triggered which extracts the meaningful values, so it applies algorithms and stores the results in the corresponding database. And this database is then accessed from our customers or the application and shown to our customer. We also have the possibility to analyze the raw data with this setup. And as soon as you know which algorithm you want to apply, you have to change the setup slightly. So that means you don't apply the algorithms in the cloud. If you know what you want to apply, you apply it on the industrial PC. That's the only change in the setup. And this means you reduce drastically the amount of data which need to be sent to the cloud. So you only send the results and not the full raw data, which is sampled on a high sampling rate. And the rest stays more or less the same. And now I want to show you an example of an algorithm which we can apply, and as Gerrit already mentioned, one issue our customer had was squeals, they had some complaints that it was too noisy, and they wanted to figure out where the squeals occur and to take actions to prevent the squealing, for example, grease the tracks. And therefore, we applied a rather simple algorithm, but it was good enough to solve the issue, and that's why you don't need to overcomplicate things if you can do it simple. So this is the algorithm. You have a raw signal, acceleration, and then you apply the frequencies corresponding for the squeals. You filter the signal in the frequencies which are corresponding for the squeals, and then you compute the energy of the signal. And if this energy of the signal is above a given threshold, it's detected as a squeal, and the GPS position together with the timestamp is stored in the database as a result. And this is now what we present to our customers. So it's a heat map, and the red areas indicate areas where you have a lot of squeals, and the green areas or areas without any color has no squeals. And to validate our algorithm, we had some positions where a lot of complaints happened, and we were able to map our positions we found to the complaints from our customers. And these positions are indicated with the green and the red dot. You can see it best on the right lower side. And that was the first example, and the second example is the rolling stock health, more precisely the wheel health. And therefore, we applied the Sebstrom analysis, which we found in a paper which is cited here on the slide. And this Sebstrom analysis finds repetitive pattern in a signal. And the more prominent this pattern is, the higher will be the amplitude. It's more or less similar to a spectral analysis. So, and that's how we apply the algorithm. So we break the raw signal down in different windows of a given time span. Then we apply the Sebstrom, which you can see the blue plot, 1D plot in the middle. And if you have a peak there, you know this is the amount of sample it takes till a signal repeated itself. So in this case, it's roughly 7,500 samples, and you have a high peak. And then we plot this in a vertical direction so that you can see the evolution over time of this Sebstrom. And now you just need to figure out where you have to look in the Sebstrom for a peak and map it to a part. And in our example, we need to find the time it takes till this wheels took one full revolution. So this is directly correlated with the geometry of the wheel, so the diameter and the speed of the train. And with this information, you can calculate how many samples it takes. So in our case, it's 7,500 roughly, and if the train goes lower, less fast, it takes more samples till the signal repeats itself, and if it goes faster, it takes fewer samples till the signal repeats itself. So it's inverse of the speed, as you can see here on the slide. So now we know where we have to look for the peak, and this is here indicated with the blue and orange border. And between, you can see a white line, which is the signal that comes from the wheel. So this is the repetitive signal of the wheel. And the higher or the brighter this white line is, the more prominent is this signal. And this means the health is worse of the wheel. And to validate our algorithm, we use the maintenance window of the wheel set. And we compared before and after. So our hypothesis was that before the maintenance of the wheels, the wheel condition is worse, which means a higher value of the wheel index. And after the maintenance, it should be lower. And here you can see the data sampled for a few months before and after the maintenance in the violin plot. As you can see, the blue violin plot is higher than the orange one, which means our hypothesis was proven true. What I also want to emphasize here, that does not mean that wheel was in a really bad condition because it was a scheduled maintenance, so it was still good, but we were already able to pick these differences up and to show to the customer what we found here. That was it from my side.
Thank you very much, Stefan. So we're already at the summary. So once again, let us recap what we saw today. So the motivation has to be the motivation of the end application with such things that we do. Whether it's measurement technology or data science, there has to be the why first. And this is, in our case, one more time, safety, reliability, ecological compatibility, and of course, lower total system costs for the rail system at hand. And in this case, it was actually the environmental factor with the complaints about noise that triggered the need for this collaboration. Condition-based maintenance, as I think all of us here know, is a chance to realize, let's say, some savings in the costs. However, what I would like to add there or emphasize one more time, the system for conducting condition-based maintenance also has a price, and you have to look at it in individual cases every time. In our case, the main challenge was to get the entire system to work. So we came from a place where there was no sensor mounted on a train to mounting the sensor, cabling it, installing all of the hardware, getting that up and running, connecting to the cloud, building the cloud architecture, and then the algorithms on top. So that's, let's say, a very large chain, and getting everything to work together and getting to an end result which is finally interpretable is quite a challenge. And you start with problems which are sometimes not very high-level problems, but very practical ones. So in this case, we developed this proof of concept with AVA. So one more time, also, we want to thank them for the initiative, for the idea, and the inputs for honing that use case with us together. Also, I want to emphasize the special role of visualization. Let's say an acceleration signal on its own does not convey a lot of meaning to humans or to a rail operator. So you have to do some work in order to translate that into something that they can actually work with. So this heat map, which we've seen, is intuitive, understandable immediately, and they were able to derive some conclusions from it on where to alter their lubrication strategy, let's say. And then also for this wheel health index. So this all comes from a time series at 50 kilohertz acceleration, and then we end up with something that is either higher or lower depending on the state of the wheel. So this is our interpretation of the role of visualization and how that is at the end the value which the customer needs or the application needs. So as an outlook, we are still working on this actively. We are happy to to open ourselves for more collaborations in academic area. Maybe some of you are from the rail sector and are interested in such a system. So we are open to talk with anyone who has inputs or wants to explore together. Thank you very much.
Thank you very much. We have time for questions. I didn't know there is an English word for Kurvenkreischen, but you found it in Leo.
That's the squeal.
Kurvenkreischen. What you mentioned, it's tricky to deploy these kind of systems on a train. But is it regulations, or are there special rail regulations for a computer and the sensor, or what's the problem there?
There are multiple. I mean, if you want to industrialize it, it depends also on the country, of course. But there are certain, let's say, especially the electromagnetic aspects for the electronics are quite important, and there are some areas where they're very strict. In this case, there were also some constructive difficulties, i.e. how do you mount a sensor in a way that it, A, doesn't fall off, which can happen, and B, transmits the vibration still the best way. And then also, where do you place these electronics in the train? Where's the space? So it's a bunch of aspects like this, like housekeeping aspects that stand in the way of getting like nice graphs at the end like this. Yeah. So.
Questions from the audience? Frequency? You have accelerator 50 kilohertz.
So this is the data acquisition sampling rate, yeah.
So you can sense up to 25 kilohertz. You wouldn't expect interesting signals much higher, maybe?
No, I don't think so. So in this algorithm we applied, you know exactly up front how fast the train goes, how fast you need to sample, and we think it's suitable. I think it's even too high currently, but we wanted to sample it too high that we can go lower and not the other way around, that we don't see anything in the signal which we could be interested in. So that's why we chose this high sampling rate.
But Kistler offers sensor with higher frequency.
Yes, but the problem is to put the data to the cloud, because you have only a LTE connection and it takes too long, so you get behind uploading the data, and then it's not the current state which you will have in the database, because you still upload from a day ago or so.
Thank you. One last option. Otherwise, I feel now very comfortable traveling train in Aarau. Thank you very much. Well, welcome.